So before we get started, I'm going to just do a land acknowledgement for where I'm based at the University of Alberta, and then after that, I'll introduce our speaker. So the University of Alberta, its buildings, labs, and research stations are primarily located on the territory of Nahiya, Cree, Niitsitapi, Blackfoot, Métis, Nakota, Stoney, Dene, Haudenosaunee, Iroquois, and Anishinaabe, Ojibwe, Saulteaux lands that are now known as parts of Treaties 6, 7, and 8 and homeland of the Métis. The University of Alberta respects the sovereignty, lands, histories, languages, knowledge systems, and cultures of all First Nations, Métis, and Inuit. So our speaker today is Clément Hardy. Clément has been working with the Diverse Project as a postdoctoral fellow and independent researcher since the very beginning of the project. His PhD thesis concerned the long-term impacts of different forest management strategies at the landscape scale. As such, he has extensive experience with the LANDIS-II model that he used throughout his thesis. Previously, Clément has worked on a variety of subjects related to ecology, animal occurrence probabilities, modeling via camera trap data from Africa, fieldwork in the French Pyrenees for a landscape genetic study, and an ethological study concerning birds in Sweden. He's also an enthusiast science communicator who loves to convey complex subjects in simple and visual ways. So thank you so much for being with us, Clément. I'll let you take over from there, and super excited to see what you have to share with us.
All right, thank you very much, Catherine. Please interrupt me if something's not working with the slides or if you cannot hear me properly. But now, well, I will start. So thank you, everybody. Welcome to this Diverse webinar when we'll talk about the LANDIS-II simulations that we've been working on in the Diverse project. Now, I went with the theme of the Odyssey for one simple reason, that when I started writing about all of this work we've done so far for this webinar, I quickly realized how much of an enormous adventure we had embarked on 2 years ago when we started working on this. Just like Ulysses and its 10 years of journeying to get back to his home in Greece, we really didn't know it would be such a long and complex voyage. So I'll be happy to tell you a bit about our story. So as Catherine said, during my PhD thesis, I explored the long-term and large-scale effects of different forest management strategies with LANDIS-II. And this is why when I finished my PhD, Christian approached me to work in Diverse, because in Diverse, we want to explore the possibility of improving forest resilience through forest management, but we have to test that. Now, bad news, forest ecosystems are very slow compared to our tiny human lives and to the threats of global changes, and we cannot do experiments and wait 80 to 150 years for results. We need answers now. However, there are some good news, is that we now have incredible computing capabilities, so we can run some pretty advanced simulations of forest ecosystems, and that's what we are doing in the Team 4 of Diverse. So the current team of Team 4 is supervised by Marie-Josée Fortin. Preparing the model is me and Mathieu Garcia, and then we have a postdoc, Junlan Wang, and 3 students, Shili Wang, Charlotte Grieve, and Zijing Luo, who are going to run the model and do analysis on the different landscapes we're going to simulate throughout Canada. So our goal for today is to tell you what we've been doing for almost 2 years now, which is preparing cutting-edge simulations in 6 different Canadian landscapes to compare the effects of a business-as-usual management strategy, climate-smart forestry, and the famous functional complex network that you might have heard in previous webinars. So my goal is not to make sure that you remember everything about LANDIS-II that I'm about to tell you in this presentation. My goal is that you get an overall good idea of the complexity we are dealing with in exploring these questions so that you can better consider these results that you'll have from us as partners, or that you might do in your own research if you're external to Diverse, which can be inspiring if you're interested about what we've done. So we'll start by talking a bit about what LANDIS-II is, then we'll talk about the collaborative infrastructure we have to build to work together on this. Then I'll talk about the extensions that we have calibrated so far and the things we've done, and I'll finish with a quick conclusion. Starting with what is LANDIS-II. So I think many of you might have heard of LANDIS-II now, since we often talk about it in Diverse, but I'm just going to give you a quick refresher and then talk about why LANDIS-II is so complex. So LANDIS-II is a forest landscape model. It's a model to simulate the evolution of millions of hectares of forests as they are affected by natural and human disturbances, changes in temperatures, and so on. It was made in 2004, but it has been carefully updated ever since. It has been managed by a non-profit directed by researchers, the Landis Foundation. And LANDIS-II is also a modular model, meaning that it's made of different extensions to represent the different processes like natural and human disturbances in the simulation that the user can choose to use or not. And each extension has its given programmers and developers, which are most of the time ecological researchers, but the code of all of the extension is open source on GitHub and everything is free, which is great for transparency, improvements, and replicability. So LANDIS-II works by simulating a raster map, which is made of pixels. So in these pixels, we have pixels that are not forested, and we are not going to simulate them because LANDIS-II is a forest landscape model. So water, urban area, agricultural area, they just stay static. We consider them inactive. But we also have forested pixels, which we are going to simulate, in which we are going to find what we call age cohorts, which represents groups of trees of the same age and of the same species. So in a given species, you can have, for example, one age cohort of balsam fir of 40 years, one age cohort of black spruce of 80 years, etc., etc. And these age cohorts are going to grow and die according to their age, the competition for light and water inside the pixel, changing growth rate due to the temperature and to external disturbances which are happening in the landscape. However, something important to take into account is that while LANDIS-II is a spatially explicit model, each pixel has a position in space related to each other, and they represent real forests on a map. But space is not simulated when we go inside the pixels. What I mean by that is that the age cohorts, they don't have a place in the space of the pixel. They are just bags of biomass dealt with equations. The drawings I'm showing you here are, of course, an abstraction. And most importantly to remember is that the repartition of the biomass of the trees of the age cohort is considered to be even and homogeneous inside a pixel. So age cohorts, they have the great advantage of reducing computation compared to simulating individual trees. So we can simulate very large landscapes thanks to this approach. However, the limit is that because the biomass is evenly distributed inside a pixel, we cannot have spatial variation at the pixel scale, which is particularly problematic to simulate gaps inside the pixel. But as we will see later, there has been some attempts to at least simulate the presence of gaps in the canopy. We'll talk about that later. Still, this age cohort system can simulate complex age structures at the pixel level with varying cohort ages. One thing also, maybe you're asking yourself, okay, but what is the size of your pixel? Now, it's up to the user to choose. Most of the time, it's 1 hectare, 100 by 100 meter. But sometimes it's a bit bigger, sometimes it's a bit lower. It depends on the size of the landscape, of the time you have, and the resources you have to run the simulation. So now if we have all of this, as a user, you have to choose the disturbance to simulate in your landscape and, of course, calibrate different extensions. So, for example, we put forest fires, insect outbreaks, wood harvestings, and then we run the simulation. And the way that things are going to run, oh, I'm sorry, there's a bit of French in my slide. Pardon my French. The way that it's going to run is that at every time step, as you see on this animation, the different extensions are going to activate one after the other and are going to affect the vegetation inside the pixels of the landscape. So as you can see, forest fires, and then insects, and then wood harvesting, and then tree growth. It's up to the user to choose the order, of course, and the time step for each extension. So here, for example, it's 5 years. And as you can see, the landscape is going to change according to this disturbance. So sometimes they're going to happen, sometimes they're not. There is stochasticity and variability involved, especially with forest fires and insect outbreaks, because they are periodic most of the time. So yeah. So I think it gives a good visual of how things works inside the model. Now, one thing that can be a bit difficult to grasp with LANDIS-II is that there exists different extensions for the same thing. For example, there are several succession extensions that have been developed. And here, when we say succession in the LANDIS-II lingo, we mean the process of growing the age cohorts and affecting them with competition and senescence. It's a particular category of extension in LANDIS-II. And you have several of them, which represent different offers, different algorithms, different approaches, and different levels of complexity, all of them simulating the same process of tree growth and competition. I'll talk about them a bit more later in detail. And choosing the right extension, of course, for a given process, and of course, it can be succession, it can be forest fires, you have different extensions for fires, for other processes, other disturbances. It's not unlike choosing a car. You don't have to choose the biggest or the quickest car for a particular goal. If you live in a city, a Toyota Yaris is perfect. If you live in a forest, however, you might need a pickup. And that's the same thing. You don't need the most complex extension to deal with a given research question, especially because there is a big cost related to the time it will take to calibrate the most complex extensions, as we will see today. Now, during my PhD thesis, I've developed two extensions for LANDIS-II, which increased its capabilities. Magic Harvest, which allows the user to make any kind of forest management we want in LANDIS-II through scripting or external programs, and the Forest Road Simulation extensions, which simulates the creation and maintenance of forest roads after every forest operation based on topography, presence of streams, presence of lakes, of rivers, etc., etc. So all of this is making LANDIS-II having a big advantage over a lot of other models because it's capable of simulating a lot of different stuff. And especially with these two extensions, we are now capable of simulating some quite complex forest management and exploring a lot of details about forest management, which LANDIS-II at the beginning is not really made for. LANDIS-II is more of an ecological model rather than a model to explore forest management. But now we can go very, very deep in these research questions related to forest management. So last thing, what does LANDIS-II looks like? Because as humans, we are very visual animals. We want to know what things look like. And that's how it looks like. LANDIS-II has no graphical interface. It's all in the terminal like the good old days of DOS. So you just run the model and then it prints text telling you what it's doing time step by time step. All that you've seen so far are output maps of the models that I have colorized and animated. So sorry, it's not very pretty, but at least you'll have a good idea as to what LANDIS-II looks like when it runs. Now, talking about the collaborative infrastructure that we needed to set up. Why do we need a collaborative infrastructure? Well, it's because me and Matthew had the mission of preparing the model, and then Junlong and the PhD students had the mission of running the model for six different landscapes in Canada. It sounds quite simple on paper, but it really is not. So to give you a sample of the complexity that this represents, we need to make sure that a team of different people will need to use a model that has no graphical interface, uses hundreds of different files for a given simulation, with the files changing for each landscape and each scenario, of course, has thousands of parameters in total, is made of different models which can have different versions, all of them being developed and updated not by a company, but by individual different research teams. And so they can contain bugs or incompatibilities between each other. When a module is updated, it sometimes changes the format of its input, and so you have to change your input files. During the simulations, we also need some Python packages to do certain actions and to do our analysis. So we need to have these working together. And la cerise sur le gâteau, as we say in French, for each landscape, we will probably need to make thousands of simulations in different batches, during which we will progressively complexify, improve, refine the parameters and the overall approach with the feedback from our partners. And each simulation takes 30 gigabytes of RAM and can take 1 to 3 days, but sometimes up to 5 days to run. So as you see, that's a lot of complexity. And it's not just a question of making the files, calibrating everything. It's also about making sure that we keep track of everything we do to ensure transparency and replicability, and also make sure that, to make sure that everybody understands and knows how to do things on their own computer, because it's kind of technical to run this kind of thing, right? So I'm going to go maybe a little bit into the geeky stuff, not to bore you, but to show you what we've had to do to solve all of these issues with the help of some cutting-edge tech and tools. In particular, we used 5 tools and practices to make things right. The first was to document as much as possible everything we are doing, especially through Jupyter notebooks, READMEs, text files, etc. So Jupyter notebooks in particular have been really useful. They are virtual research notebooks when one can combine research notes and scripts to execute computation or analysis. It's a format that is free and open source. And in addition, by scripting what we do, like interacting with data sources to make parameters, etc., rather than doing things by hand in different softwares, for example, doing things with Excel, we can ensure both transparency and replicability in how we deal with different data sets and sources to produce our parameters and our files. And this is very, very important because this kind of knowledge is most often lost in a couple of months or years when the research is done. Here, everything is replicable, redoable, and can be shared to our partners, to reviewers, and also to future research team so that they can reuse what we have done. So in the end, every parameter we took from the literature or computed and calibrating ourselves, we noted where it came from, how it was made in detail. And again, this is not always the case in ecological modeling or with LANDIS-II studies, where the huge number of parameters or files is often a deterrent to keeping notes on everything, because as researcher, we simply don't have the time. We have also organized a pipeline to systematize the distributions of files to the students and the different person in the Team 4 team. So I'm going to take the metaphor of a cookie factory for that. So first it starts with the calibration notebooks and documentation we've done to tell where we found this and this parameter, how we've made this or this file, etc. And this is the part when you acquire the ingredients for your cookies. Then we store all of these parameters and file into what we call parameter staging folders. And these are folders when we classify things by source. So these are the things that Clément has done, the things that Matthew has done, the things that comes from this study, the things that have been shared by this researcher, etc. So it's a bit like storing our ingredients for our cookies. Then we put everything per landscape and per simulated areas into what we call simulation staging folder. So at this step, we are putting the ingredients ready to be mixed, but we have not mixed them yet because the students, the personnel of Team 4 might need these files to combine them in different ways for different management scenarios. And we don't know exactly what management scenarios they're going to do because they might do that in partenariat with their partners for the different landscapes. So here, again, it's ready to be mixed, but not mixed yet. But it is classified, separated per landscape. And this is what we are giving to the rest of the team. Then the students and postdocs are going to be able to make the simulation folders. So this is the folders where the ingredients are mixed and they're ready to be cooked. So at this point, the files are ready to launch the simulations. You just have to click on the right script and then LANDIS-II runs. And then, of course, you run the simulations, which is a bit like cooking your cookies. So what's given to the student, as I said, is the simulation staging folder so that they can do the mixing by themselves and have the flexibility to do it for their different scenarios that they're going to make. Another practice we have done is to use Docker images to ensure replicable environments. And this is because historically, LANDIS-II is installed with one installer per extension and on Windows only. And remember, all of these extensions are made by individual researchers or research teams who are not programmers, and they have different versions, and sometimes they're not compatible with each other. So when you install the wrong combinations of versions, you get bugs, lots of them. And this would have been an enormous waste of time, like to have to debug things on the different computers of everybody on the team. And so we went with a different approach. We went to use Docker. Docker is a very famous software these days. It's basically a creator and manager of virtual machines. Virtual machines are basically a computer simulated inside of your computer, which is ideal to replicate a running environment because all of the packages, dependencies, and everything your program needs, you can put in your Docker virtual machine. And you can create and share this virtual machine via a simple text file, which is called the Docker file. It's basically a text file that contains all of the commands to create the virtual machine on another computer. So it's super easy to share. It is very lightweight. You can share it by email. So the way it works is that we've used Docker to make a Docker file, which creates a Docker image. This is in Docker lingo, how we call a virtual machine managed by Docker. And the Docker image contains Linux, all LANDIS-II extensions with tested versions, and of course LANDIS-II itself, and all other dependencies that we might need for our simulations, especially Python packages, R packages, etc. And this Docker file, again, it's a simple text file, so we can just give it simply to the other students, and they can create the Docker image on their own computer. And what this means is that we have no more bugs and issues, because if it works for somebody, it works for everybody, because it's the same on every computer it is deployed on. It is also very easy to deploy updates and fixes. We just have to update the Docker file, and everybody just rebuilds the Docker image on their computer. What is great is that it has been such a game changer that other people in the LANDIS-II community are also starting to use Docker as a way to run LANDIS-II instead of the more traditional Windows installer. So this is great, and we've been collaborating with the rest of the LANDIS-II community with this. Now, we've been also using Apptainers to run LANDIS-II on high-performance computing environments. Apptainers, not to go too deep, is basically Docker, but more secure and made for high-performance computing environments. And especially, it is very easy with one command in a terminal to convert your Docker image into an Apptainer. Why do I talk about that? It seems pretty minor, but it is actually very important because Apptainers allow us to run LANDIS-II on the supercomputing clusters of the Digital Research Alliance of Canada, which allows us to run thousands and thousands of simulations. And we just could not physically do that with our own computers. Remember, one simulation, just one, takes 1 to 3 days and 30 gigabytes of RAM occupied for this 1 to 3 days. This is huge. We cannot do that with regular computers. Even really expensive computers cannot do it. So Apptainers are an essential tool in our tool set for that. Finally, we've been organizing regular workshop and internal documentation to teach the team how to run the model. This is one of the things I'm most proud of. I was really scared that because what we were doing was so complicated, so technical, taking into account the model, the thousands of parameters, the tech stuff, the knowledge to run it on your computer, that the students and the personnel would simply be confused and depressed about everything. So we organized this regular workshop to introduce everybody to the extensions and to the tools one by one. And we also made very detailed documentation about all of this, how it works, the models, the files, the scripts, the Docker images, the Apptainers, everything. And to my happy surprise, the team just went with it, like started doing simulations without almost any issue at all. And it's hard to tell you how happy and relieved this had made me. So thank you to everyone in the team of Divers for entering my workshops and taking the time to read my overly lengthy documentations. I'm so happy to see your results when you send them to me. So overall, this has all been a big success. Our team is now already at work making complex simulations and developing their own management scenarios for each landscape. And a big part of this work will be invisible to you as partners because all that you will see will be the simulation made in your province by one student. But coordinating to make simulations across Canada has been a huge endeavor and was a big part of our research in the end. So to finish this section, there is one last challenge I must mention. It's timing. Because me and Matthew, we had the choice of preparing all of the parameters and files for the simulation for all of the extensions we wanted, make things perfect, and then give them to the students. But we would have to make the team wait if we did that. Or we have the choice to make a first acceptable version that we could give to the students, not perfect, not enough for what we wanted on the long term, but so that they could start working with. Now, the choice was made for us because the team needed to start running simulation, and so we went with an iterative process of calibrating, parameterizing things, and I'm going to talk more about this during the conclusion of this presentation. So now I'm going to talk a bit about the extensions that we have calibrated and worked on so far, starting with p-net succession, which might be the most important. Now, as you remember, I said earlier that the choice of the succession extension is one of the most important in LANDIS-II because this extension is the one that makes the trees, the age cohorts, grow at each time step in the simulation and compete with each other. It's the only extension that is necessary to make a LANDIS-II simulation. You can do a LANDIS-II simulation without any disturbance, but you cannot do a simulation in LANDIS-II without the succession extension. And as I said, there are several to choose from, as we've seen. So historically, most studies in Canada have been using biomass succession, which is the simplest, but is also doing the trick for what we need most of the time. But in diverse, we knew that we needed to go the extra mile because we needed to explore the effects of functional diversity. And this means having a fine-scale representation of competition, complementarity, and interactions between trees at the scale of the pixel. So we went with the most complex of them all, p-net succession. And here my journey began. So p-net succession is an extension developed by researchers at the US Forest Service, and basically it incorporates a fine-scale ecophysiological model at the pixel scale, but it can be run at the landscape scale. And it is very difficult to calibrate and parameterize to be certain of what's produced. But it is extremely interesting how it works. I'm going to try to describe it quickly. So inside pixels, we have data coming from the climate data stream. So light, water, temperature, CO2. Light in particular is going to come in the pixel and go through a cubic canopy layer system, which is a rough simulation of how canopy gaps can exist in the canopy despite the lack of spatialization inside pixels. There's a whole article by Eric Gustafsson about this methodology that I deeply recommend. It's super interesting. Water, on the other hand, is going to go through a water bucket model that is going to compute the soil water that results from interception by the vegetation, evaporation, runoff, leakage, etc. So already quite complex, but it gets more interesting. Now we're going to see how the model actually grows the age cohorts, and it does that at a monthly time step. It is the only succession extension of LANDIS-II which does things at the monthly time step instead of a yearly time step. So for a cohort, we have the leaf area index of the different canopy layers of the cohort as computed by p-net succession. And as I said before, we have the light reaching the canopy layer through the cubic canopy model. And combined with the parameters related to photosynthesis, so for example, foliar nitrogen, etc., the model is going to compute the theoretical or maximum photosynthesis made by the cohort. But it's not done yet. We are going to reduce this theoretical photosynthesis using several reduction factors. And I really love this approach. I think it's really elegant. So these reduction factors are basically going to be a number ranging from 0 to 1, and they're going to be multiplied by the theoretical photosynthesis. So we have the effect of age. So the more the tree ages, the more the reduction factor gets closer to 0, so it's going to reduce photosynthesis. We have the effect of temperature. So the more the species is near its optimal temperature, the more the factor is closer to 1, and so keeps us close to the maximum photosynthesis. And the closer we go to the extremes, the closer we go we get to 0. The effect of soil water. So again, if we have drought or waterlogging, it's going to get closer to 1 or to 0, depending on the tolerance of the species, and other effects like ozone, etc. And after these multiplications, we get the realized photosynthesis. But we are not done yet. We are going to allocate this photosynthesis inside different biomass pools: root biomass, wood biomass, leaf biomass, which is going to affect the leaf area index of the canopy layers in return, but also the non-structural carbon, which is basically an abstraction of the sugars and resources of the trees. And that's what I think is also very interesting with this model, is that the way an aged cohort can die with pinnet succession is when its non-structural carbon gets too low. And this comes from an accumulation of months with a photosynthesis that was too low compared to the maintenance requirements of the cohort, which increase, of course, with its biomass. And so this death can happen because of a combination of factors rather than a single factor. So you can have a bit of drought, but also the cohort is getting a bit old and the temperature is not very ideal. It's a bit too hot. And then there's this, and then there's that, and maybe there's a partial disturbance that reduces the LAI, etc. And so I really like that, because this creates these nuanced causes of death from the model, which I think is a great representation of how things happen in reality. Most of the time, we know that trees die from a combination of different things rather than a single factor. So this is all great, but there is a big cost to this functioning. It's the huge number of parameters per tree species. There is a lot of them. Many of them cannot be derived from empirical data, and even the one who can be derived from empirical data need calibration to ensure that the output of the model is realistic. Now, historically, the calibration has been done manually, and it's very hard to keep track. And this leads to situations when you have a ton of little Excel files in which you have done little pieces of your calibration here and there. And like a couple of years later, when someone like me comes and say, oh, can you tell me how you got this parameter? People are like, I don't remember. Maybe the postdoc can be contacted and can tell me how he got that. Again, it's entirely understandable. Like, this is very, very, very difficult. But what we've attempted here is a 100% scripted and automatized calibration inside Jupyter notebooks, which can be replicated across different landscapes, because again, we have to do that for 6 different landscapes, which is huge. Now, this calibration has been the bane of my existence for the past year. It has been the most difficult intellectual work I have ever done in my life. It has made me a bit depressed sometimes, but it is finally getting almost done. And I'm very, very grateful to the people who have helped me on this, especially Matthew Garcia, who has always been here, but also Eric Gustafsson, who is now retired and is one of the original programmer of Pinnet Successions. And Brian Sturtevant, thank you so much for your help. Couldn't have done that without you. And again, we are almost there, so it's almost done. And I think it's going to be a little revolution in the field of LANDIS-II. I hope so, because we really needed something scripted and transparent and replicable for this very, very, very difficult and complex calibration if we want to make sure to use this model in the long term. And I strongly believe that Pinnet succession is the future of forest modeling in forest landscape models. We need this kind of complexity and nuance in landscape modeling. We need to bridge the gap between ecophysiological models and forest landscape models, and Pinnet succession is really doing that, and we have a very elegant way of doing things, in my opinion, at the least. Now, talking about base fire, which is the extension we used to simulate fires in our extension. So, of course, fire is one of the most essential forest disturbances in Canada. So we went with base fire as the simplest extension to simulate fire in LANDIS-II. It's the simplest, but it's also quite effective to reproduce a fire regime. Now, at first, we wanted to go with the more complex BFOLS extension, which have been developed by the Ministry of Natural Resources of Ontario, and simulates the feedback between vegetation and fire ignition and spread. That's what makes it much more complex than base fire. Base fire, in comparison, only takes time since last fire into account as a fuel proxy, and so does not take feedbacks of vegetation composition. That means that if the landscape becomes more deciduous, there won't be a feedback done by base fire. But going with Basefire allowed us to focus on everything else we had to do, and bfolds might be used in the future. But I also worked on a new calibration of Basefire to try to make things as great as we could, inspired by the methodology of Yann Boulanger. So Yann Boulanger is a researcher at Natural Resources Canada. He has developed in the past a system of homogeneous fire regions statistically determined across Canada. So the idea is that in each of these regions, the fire regime is kind of homogeneous. And with statistical and fire modeling, Yann has targets of annual area burned across the years, or targets, predictions, let's say, of annual area burns across the years for different climate scenarios per fire region. So for example, if I look at one given fire region, I can say, okay, in 2050, this fire region with RCP or SSP scenario of a given choice should have an annual area burn of whatever percent. So the methodology that Yann has developed, because Yann is also a user of LANDIS-II, is to change the parameters of Basefire iteratively to match the annual area burn predicted by these models, these other models, which are not LANDIS. But you have to do this across all time step, all climate scenarios you're using, and all fire regions that your landscape touches, which makes for hundreds of combinations. And this is a very slow and iterative process because you have to tweak the parameters, run the simulations, and you have to run a lot of them for quite some time because there's a lot of stochasticity and variability in the simulation of fires in LANDIS-II. So you have to make 30 different simulations, make an average of the annual area burn, compare it to this single target you're doing, and then change until you match the target, and then you have 100 other targets to reach. This is very slow. What I've done is that I've used AI models to replicate the functioning of Basefire in Python, the Python programming language, but without dealing with vegetation simulation. Because remember, again, Basefire doesn't deal with vegetation. It only deals with time since last fire. So we can just have this single variable in our pixels, and that's okay. And so that's what I've done. And this allows us to have a model that is much, much, much quicker, that we can run lots of simulations in parallel because it's so much lighter than LANDIS-II. And we can also automatize the permutation of parameters through iterations. And so we make the process of matching the targets faster and also unsupervised, but yet transparent because we can see everything that happens as it gets going. And so to give you an idea, this went from maybe 1 or 2 months of work to a couple of days and a couple of days unsupervised for 6 landscapes in Canada. So this is a small revolution in itself. And I was very, very happy of that because it gave us a great way to simulate fires. And I was also able to increase the complexity of the calibration procedure by making sure that the maps generated by the model for one time step were used as the baseline to calibrate the next time step. So if for example, I calibrated the annual area burn for 2030, then I was taking the maps of 2030 with the right annual area burn and using these as the baseline to calibrate 2035, for example. So very happy about this. And in itself, because the models of Yann Boulanger, if I remember correctly, take into account some vegetation feedback, we should have some of the vegetation feedback introduced in this calibration procedure, even though we are using a quite simple model. Now talking about harvesting. And harvesting is quite important because, as I said at the beginning, the goal of Team 4 is to prepare this simulation in 6 Canadian landscapes to compare the effect of different management strategies. That's what we are trying to do. So we need to make sure that LANDIS-II can simulate these complex forest management strategies. The bad news is that the regular harvest extensions of LANDIS-II are flexible, but they are not flexible enough to make the more funky stuff that we want to do, especially the functional complex network that is quite complex. The good news is that, as I told before, I developed an extension to fix this during my PhD thesis, and this extension can run an R or Python script, or in fact any program, even Woodstock if we wanted, to make the harvesting decisions outside of LANDIS-II and then give them back to LANDIS-II to actually make the harvesting. So the only limitation that remains with this is how vegetation is represented in LANDIS-II with a raster map and age cohort. But for everything else, we can do whatever we want. So now that we had that, we still had to create some business as usual scenarios. And because if we don't have a reference scenario, we cannot make good conclusions about new scenarios like climate smart forestry or functional complex network. So to make a correct business as usual in 6 different landscapes, all of which in different provinces, again, what we've done is that I created a unified approach using federal datasets to have a first estimation of the volume harvested in each landscape, the cut sizes, but also the choices of cut types like partial cuts, clear cuts, etc. And in parallel, we asked our partners how things were done in their respective areas, especially how they choose the type of cuts they do. And then I was able to make a script that would harvest the right amount of hardwood and softwood merchantable volume at each time step with the right cuts and the right cut sizes. Now, this is essential because we need a good realistic reference, as I said, and this Canadian-wide unified and scripted way to generate business as usual scenarios for forest landscape models is actually quite new. Like, it didn't exist, and it is now free open source for other research teams to use. And I think it's going to, again, open the way to a new era of forest landscape simulations with LANDIS-II, but maybe with others in Canada. I'm very happy about that. So just, again, an idea of what this looks like, because maybe you're a forester or maybe you work with other models and you might ask yourself, what are the kind of patterns that this approach generates? So here's an example with an area, a landscape situating in the Mauricie region in Quebec that we simulated for our partner here, the Atikamekw First Nation of Manawan. So here is a raster map with the existing protected area, and the rest of the territory, which is, as usual in Quebec, is a mix of multi-use and intensive management. So here is what replicative simulation is doing. It's the same maps I showed you before, but now let's focus on harvesting. So in red, you have clear cuts, in blue, you have partial cuts, and in green, you have clear cuts followed by a plantation of commercial species. So as you see, this makes for a quite complex pattern of forest management with the script I wrote. The algorithm is attempting at every time step to harvest the right amount of hardwood and softwood, making management decisions like choosing the right cut types depending on the forest types present that it can harvest. And also you have to take into account that all of this, and that's the beauty of LANDIS-II, is constantly and dynamically interacting with natural disturbances. You can see the patches of fire in the north, and you can see that we don't make clear cuts in recently disturbed forest fire patches because that makes no sense. So all of this is interacting. When there is an insect outbreak, it changes the biomass and the algorithm is going to look elsewhere, etc. So this is really, really great. Now, while this all sounds wonderful, we should, of course, note the current limitations. All of the decisions of the models are still quite simple. We don't take profits into account. We are still simply trying to fill up targets of merchantable wood. Also, forest roads, we simulate them, but they don't influence the positions of the cuts yet. We could do that in the future. And again, note that on contrary to Woodstock, for example, which is an optimization model, the model is not doing something optimal here because LANDIS-II is much too complicated to do optimal choices with linear programming. What the model is doing is that we are giving it some rules, some algorithm, some flowchart, and it's following them at the best of its ability. That's all that it's doing. So again, one thing that you can see that I really like on this pattern is that at the beginning of the simulation, there's a lot of harvesting in the south, and progressively it goes in the north. Why? It's because the model is still trying to harvest the same targets of softwoods, but because of climate change, the softwoods are going north and north more and more with the years. So the model has to adapt and to go north to keep harvesting its softwood targets. I love that. Now, talking about initial conditions, this is an aspect that might sound simple, but is actually quite tricky. To make your LANDIS-II simulation, the simulation has to start from somewhere. So you need to give the model a set of files, which is going to indicate the vegetation, meaning the age cohorts, in each pixel of your landscape. Now, the first idea of any forester or ecologist would be to turn to the forest inventory datasets. But they have two big issues. The first one is that they all have different formats, which means a lot of time to adapt to each. The second is that they don't have precise information about the age cohort. The best we can get with these forest inventories is like for example, the age of the overstory and understory. That's the best we can have. And not all of them have it. So what do we do? Again, we have been inspired by the methodology of Yann Boulanger's teams, thank you, Yann, which is to use sample plot data from which you extract an age cohort structure by looking at the trees in your sample plot. And then you take your forest inventory polygons and you take variables you have in common between your sample plots and your forest polygons, for example, soils, dominant tree species, etc. And you do a KNN assignation, a K nearest neighbor. It's basically an algorithm that is going to assign the entity that is the closest in variable space to the other based on variable they have in common. So what we do is that we basically assign the sample plot that is closest to what we know about this forest inventory polygon. And then we can rasterize them, and then voila, we have our map. Now, we've been trying to improve on this methodology and to do it for all of Canada, of course. And for that, we're going to use the National Terrestrial Ecosystem Monitoring System that contains many different variables to use for the KNN assignation, so dominant species, soil type, etc., etc. And we are going to use it in combination with MacPlot, a very recently released dataset from the federal government, which contains sample plot data from all across Canada, which is great. And so we're going to do KNN assignation and assign age cohort structures directly to pixels. So we don't go through polygons anymore, which is great because rasterizing the sometimes very small forest polygons can create some issues. And now it's time to conclude. I'm almost there, I promise. So first off, a little word about what's next for us. So as I've explained before, there is so much to do that we aim for an iterative process to generate a first version of the parameters and then going on from this and improving things as we go. So where are we now and what have we done so far? So we started in 2024 and we started with calibrating harvesting, calibrating base fire, as I talked about, making internal documentation and tutorial for everybody to use the model, making the Docker images, etc. Then we gathered PNet successions parameters from already existing studies, especially a big thanks to Brian Sturtevant, who helped us on that. And this is not a perfect approach because ideally, PNet is such a complex model that you need parameters calibrated for your specific study area, not a different study area. And these are study areas in the US. And we also gathered initial conditions from an older methodology, thanks to Yann Boulanger. A big thank you, Yann. It has been very helpful. And this allowed us to give to the rest of the team a first versions of parameters to run simulations for 5 of our 6 landscapes. So again, this is just a very broad, a very imperfect first version. But with this, the rest of the team were able to start simulating, start building their script, start making their scenarios, and it's very easy for them as we give them new parameters to just substitute the old with the new and make new simulations thanks to the modular structure of LANDIS-II. So now we are still calibrating PNet succession. I'm almost there on it. Then we're going to make the initial conditions as I told you about, and this will make us able to release a first version of our completely homemade parameters for our 6 landscapes. And we hope to do that by fall 2026. I think we are on a good road to do this. Now, of course, things doesn't stop here. Diverse doesn't stop here, and we don't stop here because this iterative process of improving our simulations keeps on going. The road goes ever on, and we are going to keep going, especially with calibrating other disturbances like wind flow and insect epidemics. So insect outbreaks in particular, there is a new methodology that has been developed in Quebec by a research team at the TELUC. So we are working with them to see if we can take this methodology to calibrate insect outbreaks in our different landscapes with a better method that was done before. Maybe calibrating other disturbances. Another big work that is being done by Matthew is merging PNet succession with another extension of LANDIS-II, which is the 4CS extension. And this basically is going to merge PNet with the CBM CFS3 carbon model, which is a great carbon model, very efficient. And so this should make us able to have very good carbon estimates from PNet succession while still having the great ecophysiological modeling of PNet. And also, we are going to take our partner feedback into account. We have already done this when we were working on preliminary simulations in the Manawan area. As our partner wanted to explore a specific research question, we changed this a little bit. We focused our attention on different parameters, different things of LANDIS-II, and this is what we aim to do for our different landscapes. And that's it. So we arrived at the end of this presentation. I thank you for listening, and I hope that you find this depiction of our little Odyssey interesting, if not inspiring. When Christian reached out to me to talk to me about the diverse project, I knew it would be a lot of work, but even with my previous experience, I honestly completely underestimated how much work it was. Still, it was an incredibly formative experience for me, and I think for my colleagues too. Preparing these LANDIS-II simulations across so many contexts in Canada with so many pieces of the puzzle to put together, it's really a huge adventure. So big thanks to all of my colleagues, from the amazing Marie-Josée Fortin to the ever-enduring Mathieu Garcia, and to the fantastic team who's actually making the simulations, Jun Long, Shelly, Charlotte, and Zijing. We are not completely done yet. We haven't reached our destination as to producing our final parameters and, of course, making all of our simulations. But now we are getting in view. And we hope that when you will start seeing results for our team, whether in direct exchanges with us or maybe in the literature, that you'll have a good idea of the efforts and of the complex science that has went behind it. Forests are really incredibly complex systems, and trying to predict how they will evolve is really no small feat. But by leveraging the power of new technology and software, including AI, especially, it helped for coding, even though you have to be very careful with it, as well as keeping a very, very rigorous approach all the way through. I think we are pushing our predictive power one step further to really investigate how forest management can impact forests and help forests on the long term. So with that being said, I'll be very happy to try and answer any question that might have arisen during this overly lengthy presentation. Sorry. Thank you for your attention.
Thanks so much, Clément. Like he said, yeah, this is a time to take questions. So you can either put your questions in the chat and we can read them out, or feel free to raise your hand and then I can just it'll let you speak and then you can ask your question yourself.
So I'll take a look at the chat myself.
I think we have to change the settings first so attendees can chat with everyone. Okay. Oh, we already have some hands up. Okay, I'll start off with Phil here. You should be able to go ahead and unmute and ask your question.
Yeah, hi, Clément. Thanks for that presentation and the massively complicated process of keeping that all organized. I wanted to take issue with one decision in your business as usual scenarios there, and that is that you pointed out no clear cuts after in the recently burned forest. But in many jurisdictions, salvage logging after natural disturbances is in fact a priority. So might that management option, salvage or no salvage, be considered a useful scenario going forward?
Thank you, Phil. This is a really great remark. Salvage logging, we have talked about inside the team. I think the limitation is that in LANDIS-II, when a fire of high severity takes place, basically the model wipes out the age cohorts in the pixel. So we could tell to our outside scripts, the one that are running outside of Landis and making the management decisions, we could tell them, by the way, look at what happened in this fire, and like kind of imagine that you're doing salvage logging. But basically it won't happen in the model, because in the model there's nothing left, like everything has burned into smoke. But we could make some estimations inside our outside scripts and say, okay, we have harvested a part of our target volumes, target merchantable volumes, and put them in the bins to say we don't have to harvest that anymore. But this is a great thing that I think we'll try to improve on. But we've been a bit limited, by how LANDIS-II treats with fires.
Yeah, I think this is part of the broader question of how much there is mixed severity fire, especially in the boreal and subboreal zones. So you might want to try and target the distribution of low, medium, and high severity fires in each of those HFRs, as well as just the overall area burned. And then it's typically the low severity burn areas might recover by themselves, that is, with no adjustment to the cohort structure. The high severity follows your assumptions in Landis, but the medium severity is often open for harvesting because the wood is still there, but it won't necessarily switch to a new cohort immediately. Anyway, just some suggestions to play with.
This is excellent, and I think I'm going to put that on our roadmap. I think it will depend on the priorities of the different partners, but I think, yeah, this is something like fires we would like to simulate in a much more complex way. And as you said, simulating low severity could be a good step to keeping some cohorts and so keeping some harvesting. Although, yeah, we'll have to see how the algorithm is going to detect that and do salvage logging. But since we do that outside of Landis, we are much more flexible on this aspect. Thank you, Phil.
Very good.
I think we have some questions in the chat, but
Yes.
maybe we have another hand raised.
I think that hand has been lowered.
Okay. So I'll go with Sam's question, maybe?
Perfect.
Okay. So Sam asked, are there any plans to add herbivores into this? White-tailed deer are a huge issue in Eastern Canada and the US. We haven't talked about it yet, but I think it is on our roadmap of adding more disturbances. But that's the big issue with Landis, is that you can simulate so many things. You can simulate insects. You can simulate microorganisms. You can simulate herbivores. There is an extension for that. And so, like, you could spend 10 years, 20 years trying to cram everything into the model and have to do everything perfectly. And it is a very, very difficult thing to do, especially since as researchers, we all have limited time and budget to do it. So we are trying to make the most important first with fire and succession and harvesting. But of course, again, I'm repeating myself, I'm sorry. I think it's going to depend a lot on what our partners perceive as the priority. If in a landscape, our partner says, oh yeah, we have huge trouble with browsing from white-tailed deers, I think it's something that we are going to prioritize if we can. But I don't think there has been like very solid calibration of browsing. So I'll have to see what has been done, how we can improve or take what has been done in the past. So thank you, Sam, for this question. Maybe I'll go with Alexis. So he says, you have developed extensions to simulate harvesting and roads. Can we simulate different approaches of spatial organizing from cuts, like mosaic cuts, agglomerations, etc.? Yes and no. You'll be limited by the resolution you're using. So for example, you cannot make, if you're using a resolution of 1 hectare of pixels, you cannot make, as I said, you cannot make gaps inside the pixels. You cannot harvest a specific part of each pixels, because in a pixel, everything is a bouillabaisse. It's all mixed together. It's all evenly distributed. It's all bags of biomass. So the best we could do, for example, is to lower the resolution and maybe run it on a smaller landscape, but then indeed do mosaic harvesting and things like that. And it's absolutely doable as long as you have pixels that are small enough. And thanks to this Magic Harvest extension, we can do everything we want because we are the ones writing the algorithm. We are absolutely flexible, so we can say, do this kind of special organizing. So yes, it would be possible to do this kind of things. Now going to Andrea's question regarding the peanut growth reduction and maximum photosynthesis. By multiplying many small values, you might quickly and severely reduce the maximum photosynthesis. Is that an issue? How do you solve it? Liebig's laws of the minimum, maybe. I don't know about Liebig's law. Maybe I should. I'm sorry if I don't. But most of the time, yeah, of course, you're going to see it very quickly, right? If you have too many low values, your cohorts are just not going to grow and they're going to die. So that's part of the calibration of Pinette. You have to equilibrate these different forces so that your cohorts are going to grow and that they are going to grow in a way that is realistic, producing amounts of biomass that looks like what we can see in reality. It is a challenge, and that is why there has been different ways of calibrating the model that has been proposed. For example, calibrating the drought and waterlogging parameters, the ones that are going to tell you when the effect of water is 0 or 1. You have many different ways of doing that. You can choose different water pressures to try to indicate these kinds of differences in tolerance. It is a big challenge, but at the end of the day, most of the time, the model is going to still have water pressure in the soils, and your trees are going to have a big range of water in which they can grow pretty well. Same thing for temperatures, same thing for light, not light, because light is not a photoreduction factor, but same thing for CO2, etc. So yeah, there are a lot of reduction factors, but most of the time, you create ranges of tolerances for your trees that are large enough for it to all work out. Kevin has not a question, just an appreciation. Thank you so much, everybody, for your very kind words regarding the presentation. It's very appreciated. All right, do we have other questions, maybe?
We probably should wrap up anyway, since we're just past the hour, and it looks like there's no more questions coming through, so that's all perfect.
All right.
So thank you again, Clément, for presenting. This was awesome. Great to hear more about Landis and understand it a bit more. So yeah, thank you everyone who joined us and attended or not in person, just attended, and stay tuned. We're going to have a bit of a break over the next couple months during the summertime before our next webinar, but stay tuned. We'll do something in the fall, and we'll email you all with the information when that's kind of settled.
All right. Thank you, Catherine. Thank you, everybody, and have a good day, you all.
Bye, Clément. Thank you.
Bye-bye.